Thank you for the introduction. So I'm Daniel Grimmer. I used to work at the University of Waterloo, actually, with Jose, and then I switched recently to doing philosophy of physics at the University of Oxford. So this is technically a philosophy talk that I'll be giving you today. It's exactly about the topics that were just discussed in the last couple presentations, and so I thank you guys for setting up all that great context for this. So let me tell you about the pragmatic QFT measurement problem and the need for a Heisenberg-like cut in QFT. And you can see that here on this archive post. You can find that link there and at the bottom of the page, but let me just jump into it. So what is this pragmatic QFT measurement problem that I'm talking about? There's something which is fairly deeply wrong with at least a common methodology for making concrete experimental predictions from quantum field theory. Without a very satisfying theory to experiment link, which the last couple talks have been trying to get at in a way, that we're at risk of losing any right to claim evidential support or worse, physicality for quantum field theory. And now that's a fairly bold claim that there's something very wrong here, and one might be skeptical about that. What do you mean QFT has some pragmatic disconnect with these severe consequences? QFT has made so many fantastically accurate and precise predictions. For example, the muon G-2 experiment is confirmed to some number of parts per million. If something were rotten or ambiguous in the way we were making predictions from QFT, it would be a miracle if they came out so well, and the theory came out so well confirmed, right? And so that's a very reasonable thought on that. I have something more methodological in mind than just get straight accuracy of predictions. And so by analogy, I'd like you to think about the sophomores quantum theory. And now this is non-relativistic, what I'm talking about now. This is what students do after they're told to shut up and calculate. Given some initial input state, we apply some given unitary operation and then some given projective measurement. And then by some way, we do some computation, and this unambiguously gives us a statistical prediction of the experiment's outcomes via Born's rule there, right? So you can do all this mathematics and you can get a prediction out of your thing. But many physicists and philosophers are both dissatisfied with this sophomores quantum theory in that it lacks the right kind of connection between theory and experiment. And you don't have to be too philosophical about that. This is even at a very purely pragmatic level that there's an issue with the sophomores theory. So right, the sophomores theory can give you unambiguous predictions from these mathematical objects, but these mathematical objects have not yet themselves been suitably connected to our real life experimental setups. I mean, you show the sophomore a piece of lab equipment and you say, in modeling this lab equipment, which projector am I supposed to use and when? They in general have no answer to this once you take their problem sheets away. So often the sophomore might intuitively guess which projector to use and when. I mean, when we think about the double slit experiment and we have the electrons get to the fluorescent screen at the end, it's completely intuitive that there's a position measurement that happens when they hit the screen, right? And so we have this very strong intuition that that's what happens. But ultimately, that's just a guess. And that guess may consistently give us accurate enough predictions. We are very, very good at guessing the right projector. I'm not doubting that. And that does give an accurate result. But ultimately, it's nothing more than just a guess. And if we want to be more methodologically sound about these things, we need to give a model of the measurement process, right? And so this is highly problematic, even at just a pragmatic level. Ultimately, we need to give a model of the measurement process, and the same thing holds in QFT. Absolutely. So, and the last two talks have spoke to this point, right? So where do we stand on these sorts of pragmatic worries I'm talking about now? Actually, for non-relativistic quantum mechanics, as I'm going to argue a little bit later, these are all sorted out, and they're sorted out in terms of measurement chains and the Heisenberg cut. So in this context, in the non-relativistic context, there's really no more pragmatic worries left. And the quantum measurement problem becomes synonymous with more philosophical worries, right? That's why when you say quantum measurement problem, people think of philosophy because all the pragmatic concerns are handled there. But in QFT, as I think we've seen, there's big trouble ahead here. What we can't do is we can't straightforwardly transplant our old quantum measurement theory, the projective one, over into QFT. We need a new or revised measurement theory for QFT. And again, the last couple talks have spoken to this point. But this sort of scenario is the pragmatic QFT measurement problem. We need a much more concrete way of getting experimental predictions out of our quantum field theory experiments than what's going on in common practice presently, right? So here's the scope of the talk. I've told you what the problem is, what's rotten in QFT measurements. Ian's told us a bit about this. Then I'll talk about measurement chains and cuts and how we get around these issues in a non-relativistic context. And then I'll talk about what's going on in QFT, right? So why can't we just use the old theory? We have a good projective measurement theory for non-relativistic quantum theory. Why can't we just carry that over into QFT? Well, the stock answer in the literature, and it's been talked about today already, is that there are some non-trivial mathematical differences between QFT and non-relativistic quantum theory. Namely, we're working with fields now, everything's second quantized. We have a new Lorentzian causal structure to deal with, and we have new algebraic structures, being a type 3 versus a type 1 von Neumann algebra. And all of these reasons prevent us from directly taking our non-relativistic quantum measurement theory over into QFT. Right? So we can't use the old theory. And Ian already told us about these Sorkin impossible measurements here. So actually, I think I'll skip over this slide, but there's the point is that in QFT, these projective measurements you do have to be physically as well as mathematically possible, or else you get these Sorkin-like issues of O2 enabling some signaling from O1 to O3. But suppose that we identify all of those projective operators in QFT, which are relativistically safe. And Ian told us we can do this for real scalar QFT. That's a great thing, and that's a really helpful toolbox for identifying what's possible. But that, at best, what that's going to give you is a full menu of which projective measurements to choose from are available to choose from when modeling our measurement processes, right? But which of these relativistically safe projective measurements corresponds to which lab operation? That's still a bit unclear. And so yes, beyond we have these non-trivial mathematical issues, but past that we have a deeper methodological issue that we still need to model the measurement process, right? And this here's ultimately the same issue that we had with the sophomores quantum theories, that guessing which projector corresponds to our experiment, our concrete real life experiment, just guessing isn't good enough for this. And so we need something more if we're going to give a more robust answer to the pragmatic QFT measurement problem. And so I've mentioned these things have been solved more or less in non-relativistic quantum theory. And so how did that work? So now I would like to just quickly outline the story, which begins with measurement chains and Heisenberg cuts and ends with decoherence theory and projective measurements. And the main lesson I want to put out with this talk is that we shouldn't transplant the end of this story, i.e. the projective measurements, over into QFT. We should rather start from the beginning and transfer measurement chains over into QFT, and then we can see what theory, if any, we're led to. That's the main lesson of the talk, right? So what's a measurement chain? A measurement chain, or at least a very sequential one, has systems interacting. A interacts with B, and then B with C, and C with D, and so on, right? You might have an atom you're interested in interact with some light, and then a photomultiplier, and this triggers a small current, and that causes a transistor to turn on, and lots of things happen, and it ends up at a computer screen, right? And each step in this chain might be modeled in a quantum way or a classical way. And a pragmatic Heisenberg cut occurs wherever along this measurement chain we switch from a quantum to a classical model. I'm not saying the world changes its status at that point. This is just how we're modeling things, right? And here I've got a measurement chain for a two-slit experiment that I talk about in the paper, but we don't need to go into details about that. The point here is that there's going to be multiple options available for where along this measurement chain we're going to place this cut, right? So the red line on top opts for a classical model whenever possible. And so it stays classical as long as possible. And then there's a point in the middle where we deal with the electrons as they're diffracted through the two slits. And that really has to be described in a quantum way, where you get the experiment entirely wrong. So in the middle, we have to use a quantum model for this experiment. And then at the ends, we can go back to classical. But now the bottom line here opts for a quantum model whenever possible. And again, some feasibility concerns make us use a classical model at the start and end of the experiment, just because we can't feasibly do these computations on our present day, abilities technologically. And it's worth stressing here that I'm really concerned about real life experiments. My friend has done a literal real life experiment. I want to go through and actually model every part of that experiment from beginning to end, right? So it all has to be really technologically feasible presently. because I want an explanation now for the experiment. I don't want to be confirmed that one could exist if we had a nice enough computer, right? Okay, so in general, we're going to have freedom in choosing where and when to take this pragmatic cut. And that's ultimately not an issue, because the goal with explaining an experiment is not to give an unambiguous prediction of its results. It's to give predictions within the error bars of the actual experiment, right? So we're allowed to make approximations and things when we're trying to give an explanation for what a measurement is. Right. Okay, so we have options in the location. We also have options in the kind of cut we can take. Here I've got two examples that I talk about in the paper. First, we have a diagonal cut. So here we have two systems, A and B, adjacent on the measurement chain. And we model one of them in a quantum way and the other one in a classical way. We have a direct dynamical coupling between these two theories. So that's one way you could cross the cut. The other way is three systems, X interacts with Y, described in a quantum way. Then Y in isolation, we apply some approximation scheme to it to get a classical description. And then we continue on in a classical way after this. So this is a vertical cut, and it happens to a system in isolation, right? And the goal here, let me again stress, is an actual, tractable, connect the dots, model-to-model account of real-life experiments. That's really what I'm trying to drive towards now. And however and wherever we do take this pragmatic Heisenberg cut, it ought to be done intentionally and explicitly if we're being very careful about things. But when we think this way in terms of measurement chains and cuts, what it gives us is for each individual experiment, it gives us a roadmap for modeling that experiment's measurement process. And these dangerous areas about crossing the cut are all clearly marked out ahead on this roadmap. And we've got multiple different options for how to get around them in explaining this individual experiment. And so just using the tools I've talked about already, we have a case-by-case basis for giving good models of quantum experiments. And this is already a measurement framework, right? I'm not going to call it a measurement theory, but it's a measurement framework. And notice I haven't talked about decoherence theory or projective measurements at all yet. Those are not relevant at all at this point in the talk, right? So this case-by-case measurement framework that we have, it already mostly solves the pragmatic measurement problem. And I hope you'll admit it's a lot better than the sophomore strategy of just guessing which is the right projector. So, but we might further want a wide-scoping unified measurement theory. What I've talked about till now is just case-by-case. And to achieve that, what you need is a near universally available way of crossing the Heisenberg cut. I'm still dealing everything non-relativistic at the moment. I'll make it into quantum field theory in a moment, right? It's only when we want to take this framework and unify it into a proper theory, the decoherence theory and the Born rule become special. And this is what takes us from a case-by-case measurement framework to a unified measurement theory, which turns out to be projective measurements, right? So now let's apply this to QFT. My lesson is we shouldn't take the end of this story, the projective measurements, and try and fit them into QFT. What we should do is start from the beginning, talk about measurement chains and cuts, and put those into QFT. And then we can see what theory we're led to, if any, right? So when we move over to QFT, basically nothing changes in the first part of the story. A pragmatic QFT cut, I used to call it a relativistic cut. I've changed my terminology some, so that's what the confusion might be. But a pragmatic QFT cut occurs wherever along the measurement chain we switch from a QFT model to a non-QFT model. And as before, we're going to have multiple options about the location. We could take that to be diagonal or vertical. And alone, this is going to give us a measurement framework for QFT on a case-by-case basis, right? The question then is, do we have some near universally available way of making QFT cuts in a way that would underwrite a measurement theory? And to that, we need to go look at the physics literature. And as in the non-relativistic case, you could either take a diagonal cut or a vertical cut. Here is shown, and here is a horizontal move that I also discussed. And you can do this sort of thing with the Fuster-Wirth framework, as Max just told us. You can do very careful steps in the measurement chain where we go from a QFT to a QFT. Those can be done very carefully in the Fuster-Wirth framework. But I'm suggesting that for a complete description of the measurement chain, at some point you have to take this QFT cut. And this is what Max was saying when he said that he assumed his experimenter has full access to the QFT probe. Well, that full access means being able to describe it with either a diagonal or vertical cut at some point when we do further processing of that. Right. So in a diagonal cut, we're going to have a QFT interact with something which is not a QFT. And in a vertical cut, we're going to have QFTs interact with each other a while, and then we'll take an approximation on the QFT, which gives us some non-QFT system, and then we continue on describing the experiment from there. So let me first talk about the vertical option. So how well do these vertical cuts preserve the central commandments of relativity, covariance, and causality, and locality? If done correctly, then within well understood and controllable errors. And that's all that we need. Again, approximations and controllable errors are allowed here. We just want an explanation within the error bars of the actual experiment, which is going on. Right? And how well do these approximations connect with experimental practice? This is where we run into some issues. The concrete applications of these vertical moves are actually rather limited. If we want to jump vertically up onto a first quantized atom, then what needs to go below it is a second quantized description of an atom, which we can't yet model well in QFT. Interacting bound states like the hydrogen atom aren't really accessible to us. Let me just say, so if in slot something number 2, we want to put a first quantized hydrogen atom, what has to go below it in slot QFT number 4 is a second quantized hydrogen atom, which we really just have no technical grasp of at the moment, right? So let me skip over that point. Right, we can also consider diagonal QFT cuts here, and an exemplar of this is the Underwidth detector model, which people may or may not be familiar with. So in the Underwidth detector model, a non-relativistic atom-like probe is coupled to a quantum field. For example, here is a Lagrangian where we have an Underwidth detector coupled to a massive Klein-Gordon field. So here's the Lagrangian for the massive Klein-Gordon field. We have a free Lagrangian for the Underwidth detector, which is something atom-like. You can imagine it as being like an atom. And then we have a coupling term here, which is a lot like the coupling term that Max showed us. The only difference is this mu hat here is not a field operator. It's an internal degree of freedom of the Underwidth detector. But like with what Max said, we have some compact region K, which we could support this interaction profile over. And this induces an interaction between the relativistic system and the non-relativistic system, right? And for point-like detectors, what you can do is take the smearing function to be localized on a trajectory with some switching function in time going on. So you can take these Underwidth detectors to be point-like. And so how well do they connect with experimental practice? They actually do extremely well. The Underwidth model is a very close model for the light-matter interaction, and it improves upon what's done in quantum optics. It also gives, you can also use it to model the effect of a graviton on an atom. In this way, you can build fermionic particle detectors this way. And all of this story about Underwidth stuff can be done in curved spacetimes as well. And there's so many different computations which are done with these tools. It's really quite impressive. But now on to maybe the main skepticism about Underwidth detectors. How well can they preserve the commandments of relativity? They're going to break covariance and locality. I mean, certainly they're a non-relativistic system coupling to a QFT. And that's true. They preserve these things imperfectly, but again, within well understood and controllable issues. For point-like detectors, there are essentially no problems. And we can talk about that a bit later if you like. But for smeared detectors, so it's Underwidth detectors with a finite width, you do get Sorkin-like measurement issues as sort of the information comes in the left edge of the detector, skips over to the right edge, and is emitted there. So you can have the signals jumping forward a little bit in a acausal way. But in practice, that's actually not much of a concern, because when that's relevant is when you care about timescales down to the light crossing time of the atom. And if you care about that, then you actually can't describe your atom in a first quantized way anyway, which is the regime where an Underwidth detector would make sense. So it breaks down exactly when you expect it to as a model of an atom, right? So it just has its domain of applicability, which is not everything. Right. Okay, so can we do enough with these tools? So in my assessment, these tools that we have, the Fuster-Virch framework, the Underwidth detectors, and some approximations, each of them has their limitations and needs some more development. They need to be connected with experimental practice more in some cases. But together, I think they have a substantial scope and can do basically any experiment we need them to. But of these, the Underwidth detector, I'm arguing, has by far the widest scope of applicability in terms of actual experimental practice and actual ability to explain actual experiments, right? So it has the widest scope of any of them. And so if we want a wide scoping measurement theory for QFT, which applies to actual experimental practice, then this is the best way to go, I think, is to base things on under DeWitt detectors. And in a detector-based measurement theory for quantum field theory has been proposed by our chair, Jose Polo Gomez, and Luis Garay, who I think is in the audience, and Eduardo Martinez. They put out a great paper using this sort of under DeWitt detector approach to get at a measurement theory for QFT. All right. So in conclusion, yes, there are technical issues with transplanting our projective measurements over into QFT. However, there's a deeper methodological issue. We need to give concrete models of the measurement process, and those need to be computationally tractable so that we can actually use them to explain experiments right now. We ought to better understand measurement chains and Heisenberg cuts in QFT. Measurement chains already give us a measurement framework. If we want something additional to get a measurement theory out of it, we need to do some more work. And I think under DeWitt detectors are the current best hope of giving a wide scoping measurement theory for QFT. Okay, so thank you for your time.